Hi there. Today we're going to walk through a realistic DevOps interview focused on caching, queues, and backpressure. These are the core mechanisms that keep modern systems responsive when traffic spikes, upstream services slow down, or workloads become unpredictable. I will ask you a mix of behavioral and technical questions, and after each one, I will give you a sample answer so you can compare your thinking. If you want the full benefit of the simulation, pause before each answer and try to speak your response out loud. If you find this helpful, subscribe so you do not miss the next interview session. Let's start with some behavioral questions to understand how you think about reliability, performance, and system design under pressure. Tell me about a time when you used caching to solve a performance problem. What was the issue, and how did you decide what to cache? A strong answer might sound like this. I had a service that was repeatedly fetching the same data from a backend API. The API was reliable but slow, and as traffic grew, the latency became noticeable. I looked at the access patterns and realized the data changed infrequently, so caching made sense. I implemented a short-lived in-memory cache and later added a shared distributed cache so multiple instances could benefit. The key was validating that the data was stable enough to cache without causing stale results. Once that was confirmed, latency dropped significantly, and the back-end load decreased as well. Next question. Describe a time when a queue helped you stabilize a system under heavy load. What was happening and what role did the queue play? A solid answer would be, we had a batch of user requests that triggered heavy processing in the back-end. During peak times, the system slowed down and in some cases, timed out. I introduced a message queue so requests could be accepted quickly and processed asynchronously. This let us smooth out the load and handle spikes safely. It also gave us better visibility into the backlog. The final improvement was adding more workers to the queue so throughput matched traffic patterns. The queue acted as a buffer and prevented users from seeing failures during busy periods. Next, behavioral question. Give me an example of when you had to handle backpressure in a system. How did you detect it and what did you do? A thoughtful answer could be, I started noticing that our downstream service was responding slowly and our request queue was growing faster than expected. Latency in the upstream service kept rising. That is a classic sign of backpressure. I added rate limiting on our side so we would not overwhelm the downstream service. I also reduced retry attempts and added a timeout that aligned with realistic service expectations. Once we smoothed out the traffic, the entire system stabilized. The key insight was treating slow responses as seriously as failures. Next question. Tell me about a time you removed a cache or reduced caching levels. Why did you make that decision? A good sample response might sound like, we had a cache that was masking the impact of a slow database query. The cached data was fresh most of the time, but when it expired, users would suddenly experience large spikes in latency. Instead of raising the cache duration, I fixed the underlying query. We optimized the indexes and adjusted the data model. Once the database performance improved, we reduced the cache retention to keep results more accurate. The decision was driven by the desire for reliability and correctness, not just speed. Final warm-up question. Describe a situation where a queue became a problem instead of a solution. A realistic answer would be, we had a queue that absorbed traffic spikes very well, but it also hid the fact that our workers were gradually falling behind. The backlog kept growing until it reached its maximum size. The delay became unacceptable. The real issue was insufficient worker throughput, not the queue itself. We added better monitoring on the queue depth and worker processing times, then scaled the workers and optimized their logic. After that, the queue returned to being a buffer instead of a bottleneck. Let's shift into the first half of the technical and scenario questions. Explain the difference between a read-through cache and a write-through cache. When would you choose one over the other? A clear answer might be, a read-through cache loads data into the cache on demand. If the data is not cached, it pulls from the source and stores it. A write-through cache updates both the cache and the underlying store when data changes. I choose read-through when I care most about reducing latency on reads and the underlying data changes infrequently. I choose write-through when data consistency is critical and I want the cache to always have the freshest values. Each pattern has trade-offs around latency, correctness, and complexity. Next question. Imagine your service calls an API that becomes slow during peak hours. You want to add caching, but the API data changes constantly. How do you decide what can and cannot be cached? A strong answer would be, I analyze which parts of the API responses are stable and which are dynamic. Often, not all fields change at the same rate. I might cache only metadata or derived values while fetching time-sensitive data directly. I also look at user tolerance for slightly stale data. Sometimes caching for even a few seconds can dramatically reduce load without hurting correctness. The goal is to break the response into pieces that have different caching needs. Next scenario. Your queue is growing rapidly. Workers are processing tasks, but not fast enough. When do you scale the workers, and when do you redesign the system? A thoughtful answer is, scaling workers is the first step if the workload is parallelizable and the tasks themselves are not too heavy. But if the queue keeps growing even after scaling, the root cause might be inefficient task processing or an upstream service causing delays. At that point, I consider optimizing the worker logic or breaking tasks into smaller units. Redesign is needed when the workload does not scale linearly with additional workers or when another dependency is the bottleneck. Next question. Explain backpressure and why it is important in distributed systems. A solid answer could sound like, backpressure is the system pushing back when it is overwhelmed. It signals to upstream services that they need to slow down. Without backpressure, upstream components would continue sending requests at full speed, causing timeouts, queue explosions, and sometimes cascading failures. In other words, backpressure protects systems from themselves during high load or degraded performance. It is essential for stability. Next scenario. Your API uses caching to avoid hitting the database too often. Suddenly you notice lower database load but higher latency on some requests. What do you check? A strong answer would be, I check for cache misses that lead to slow database queries. If the cache hit rate is too low, some users might get the slower fallback path. I also check if the cache itself is experiencing high latency. A distributed cache can become slow if the network is congested or the cache cluster is under stress. Finally, I look at whether the cached data size is too large, causing serialization overhead. Caching can hide some problems while creating others, so the full chain needs inspection. Here is the next scenario. You add a cache to reduce database load. It works at first, but after a few days the cache grows very large and eviction rates spike. Suddenly performance becomes unpredictable. How do you approach this? A strong answer would sound like this. I start by checking what is actually being stored in the cache. Sometimes the key space is larger than expected or the cached objects are too big. If the cache contains highly diverse keys with low reuse, then the hit rate will be low and eviction will constantly churn useful entries out of memory. I measure the hit rate, miss rate, and eviction rate to understand the pattern. The next step is questioning whether everything in the cache should be cached. Sometimes selective caching is more effective than caching everything. I might introduce expiration policies tuned to data access frequency. If the underlying issue is a lack of memory, I may need to scale the cache or reduce object size. The important thing is focusing on reuse, not just volume. Next question. Imagine your queue workers depend on an external API. That API slows down during peak times. As a result, your workers slow down and your queue begins to back up. You could scale the workers, but the API might not handle the extra load. What is your strategy? A thoughtful answer would be, scaling workers does not help if the bottleneck is the external API. The real issue is that the queue is feeding work faster than the downstream dependency can process it. I start by adding internal rate limiting to the workers, so they never exceed what the API can safely handle. I also add intelligent retries with jitter, so failures do not become synchronized. If possible, I batch requests so fewer API calls are made. Another option is to classify tasks by priority. so essential work is processed first while non-critical tasks wait. The goal is to prevent the queue from overwhelming a slow dependency and triggering a cascade of failures. Next scenario. You implement write caching for performance. Everything works fine until your system experiences a sudden crash. After the restart, some data is missing or inconsistent. What do you investigate? A clear answer might be: write caching improves speed but introduces durability risks. If the system crashes before the write is flushed to the underlying store, the data can be lost. I start by confirming the write policy. If it is write back, the cache keeps the data temporarily and writes to the store later. That is risky without proper durability guarantees. I also check whether the cache storage itself is persistent or ephemeral. If it is in memory, everything in the buffer is gone after a crash. In this case, switching to write-through or adding journaling might be necessary. The core idea is understanding the durability guarantees and adjusting the caching approach to match the correctness requirements of the system. Next technical question. Your system uses both a cache and a queue. Under heavy traffic, the cache hit rate drops sharply and the queue fills up. This combination creates a feedback loop where everything slows down. How do you break the cycle? A solid answer would be: this pattern suggests the system is under sudden load that the cache cannot handle. When the cache misses, the database is hit more often. As the database slows down, workers take longer and the queue grows. The key is stopping the amplification. I reduce pressure at the entry point by rate limiting or shedding low-priority traffic. I increase cache hit rate by preloading or warming the most common keys. If the backlog is large, I may temporarily increase worker count, but only after stabilizing the underlying database. Caching and queuing need to be aligned. A weak link in one will impact the other. Next scenario. You have a long-running task processed by a queue worker. The task takes several minutes and blocks the worker. During peak traffic, this causes the queue to fall behind. How do you redesign this? A strong answer would be: long-running tasks are dangerous in queue-based systems because they tie up workers for long periods. I break the task into smaller steps that can be processed independently and more quickly. Each step becomes its own queued job. This reduces the processing time per job and increases parallelism. If splitting is not possible, I consider running the long task outside of the main queue in a separate dedicated worker pool so it does not interfere with normal traffic. Another approach is offloading part of the task to a more scalable service. The key is preventing a single heavy job from blocking the entire system. Final question in this section. Your cache uses a time-based expiration policy. During a traffic spike, many entries expire at the same time. The backend suddenly gets flooded with requests and slows down. How do you fix this? A mature answer would be: that is a classic thundering herd problem. When many cache entries expire at once, all clients rush to refresh them. I stagger the expiration by adding randomness to the TTL so entries expire at slightly different times. I also consider switching to a lazy refresh model, where only one request triggers the recomputation, and other requests wait. In some cases, background refresh can help, so the cache is updated before expiration. The objective is avoiding synchronized cache misses that overload the backend. Let's move into the pressure section. These questions are designed to test how you respond when information is unclear. Systems are deteriorating, and decisions must be made quickly. Your queue backlog suddenly spikes to 10 times its normal size. The workers are running, but throughput has collapsed. You cannot immediately tell if the downstream service is slow, if the workers are overloaded, or if the incoming traffic has surged. What is your first move? A calm, thoughtful answer would sound like this. My first move is to stop the backlog from growing even larger. I apply temporary rate limiting at the entry point, so we stabilize the system. Once incoming traffic is under control, I check the worker processing time. If workers are taking longer than usual, that suggests a downstream slowdown or a new bottleneck. If workers are processing at normal speed, but the queue keeps growing, that means the incoming rate is too high. The key is stabilizing first, diagnosing next. I never let the queue grow unchecked because that causes cascading latency issues for the entire platform. Next scenario. Your cache layer suddenly becomes unavailable. All requests begin hitting the database directly. Latency surges and the database is starting to show signs of overload. You have only minutes before it collapses. What do? A composed answer might be, I reduce incoming traffic immediately, either through global throttling or by shedding non-essential workloads. Then I switch to a degraded mode where responses can be simplified or partially served to reduce database load. If possible, I enable read-only mode for parts of the application. I also restart the cache layer in a controlled way so it does not become overwhelmed during reconstruction. The goal is protecting the database above all else. If the database goes down, recovery is slow and painful, so safeguarding it is the top priority. Next question. Your workers are processing jobs from a queue. Suddenly they begin retrying failed jobs repeatedly. The retries start causing more failures and the system is spiraling into a retry storm. You do not know the root cause yet. What do? A strong judgment call would be, I immediately cap retry attempts to stop the storm. Then I pause or slow down the workers so they stop hammering the same broken dependency. Once the retry pressure is gone, I inspect a sample of the failed jobs to determine the root cause. The mistake many engineers make is trying to fix the underlying problem while the system is still generating retries at full speed. I restore stability first, then investigate. A stable system is easier to debug than one in free fall. Next scenario. Your queue is full of high-priority and low-priority jobs mixed together. Under heavy load, the low-priority jobs crowd out the urgent ones, causing delays that affect critical parts of the system. You cannot change the producer behavior in the short term. What is your approach? A mature answer would sound like this. I separate the workloads. I create multiple queues or introduce priority levels inside the existing queue. Then I assign dedicated worker pools for each priority tier. This prevents low-priority tasks from starving high-priority ones. In the short term, if I cannot redesign fully, I may temporarily drop or delay low-value tasks to ensure critical workflows remain healthy. Ensuring reliable performance for essential operations is more important than processing everything. Final pressure question. You discover that a caching decision made months ago is now causing subtle data inconsistencies in production. Leadership wants an immediate fix, but removing the cache entirely might cause a huge performance hit. How do you navigate this? A composed, realistic answer would be, I do not remove the cache suddenly because that could overload the database and create a bigger outage. Instead, I tighten the cache duration or introduce targeted invalidation on the problematic keys. I also add extra logging to confirm the inconsistency pattern. Meanwhile, I coordinate with the team to schedule a safe redesign of the caching layer. The key is balancing correctness with stability. Fixing data inconsistencies is important, but doing it recklessly can harm the entire system. My priority is protecting both data integrity and system performance while planning a permanent solution. That wraps up this interview session. These questions gave you a chance to practice handling ambiguous, high-pressure situations where caches fail, queues explode, and systems push back under heavy load. Take a moment to reflect on which scenario challenged you the most. Was it the retry storm, the missing cache layer, the runaway backlog? Each one represents a real failure mode that engineers encounter in production. If you want to keep sharpening your judgment and technical instincts, subscribe so you do not miss the next interview session.